I have some news.
Good or bad?
It's more on the good side. So what could be good news?
I don't know.
No final exam, everybody gets A.
Yes. Even we get a B, it's good. And no final exam.
All right, everybody gets B.
All right. I know Matthias if he likes that. Matthias, you like that? No?
Even those who deserve to get A plus will get B only. All right. So the news is that it's bad news on my side. Is that actually there's something I didn't cover that was needed for homework due today.
Okay. So it's not due today?
Yeah. So we postponed to Wednesday.
Okay.
So it's I think it's problem 2.
Yes.
Yeah, sorry, I didn't. We are behind in the lectures. I didn't see. All right, so Wednesday, but the next homework it will still be on due on Monday. All right, so I'm going to cover what is needed for problem 2. All right, so what is needed in problem 2 is magnitude and phase response. Okay, magnitude, and phase response. So as a reminder, so when you have an LTI system, we actually I'm going to assume it's real. So as a reminder, h of n is the impulse response. H of omega is the frequency response. Magnitude of h of omega is the magnitude response. Angle of h of omega is the phase response. All right, so the properties. So since h of omega is, what is the fundamental property of h of omega? In general, it is 2 pi periodic. Then, of course, then both magnitude of h of omega and angle of h of omega are 2 pi periodic. So that is the first important property. The second, if you find that the room is a bit dark, I switch off the light because there was sun. But if you need more light, then you can go ahead. But assuming that h of n is real, what was the property about h of omega? And I prepare my gun. H of n real, therefore H of omega. No. No, I don't shoot for that. I shoot for those who say yes. So if you know the answer that shoots you, then you are even better. So that's not the answer. It's not H of omega even. It's no. Remember that man that was an alumni of my school? Hermite, Monsieur Hermite. Hermitian symmetric, all right? Then H of omega is, okay, that's another way to remember, is Hermitian symmetric which means H of minus omega equals H of omega conjugate. All right. Now, what? So we have, if you take the magnitude, what do you say? Is the same as magnitude of H of omega. What do you say about angle of H of minus omega? All right, so we have used the fact that magnitude of A conjugate is magnitude of A, and now we want to use the fact that angle of A conjugate is minus the angle of A. And if you don't see that, you just need to see geometrically what happens. If this is A, where is A conjugate? Is here, right? So you can see the magnitudes are preserved. And you can, what about the angles? You can see they becomes opposite. All right, so here we get minus angle of H of omega. I mean what you see.
You took away that?
It's already in my bag. What is this angle? What is this angle compared to this one? It is opposite. Done. So you get this. All right. So applying this to here, you get minus angle of H of omega. Now, what is the name for this property? What is the name for this property on the magnitude response? Yes. Why are you searching far when you have something so basic? what do you say about angle of h omega? All right, now you see. Okay? All right, so when h of n is real, then these two functions have these symmetry properties, even and odd, which is basically equivalent to the Hermitian symmetry. You see, the Hermitian symmetry is equivalent to saying these two symmetry properties. All right. Okay. So now that we know the properties, we're going to do an exercise. Plot magnitude and phase responses of this system. But plot it in between minus pi and pi. Why is it sufficient to plot it between minus pi and pi? To plot them because they are 2 pi periodic. All right. And the advantage of plotting between minus pi and pi is that you can check if you will be able to check if your result is even or odd. If you plot between 0 and pi and 2 pi, you will not be able to see the symmetry about 0. All right, so impulse response, that's easy, is delta of n equals, I'm sorry, okay, I shoot myself. It's h of n equals delta of n plus delta of n minus 2. H of z is 1 plus z to the minus 2. H of omega is 1 plus z to the minus 2 at z equals e to the j omega, which is 1 plus e to the minus j 2 omega. Oh, all right. So now we want to find magnitude response and phase response. So you use the trick that we saw before. Remember this is 1 plus e to the j alpha, remember? So you can always write this as, I factor out half of the angle, e to the minus j omega, then here you get plus j omega, and here you get the remaining half minus j omega. If you don't agree with this, you go backward, and then you agree. Now here you recognize, all right, so we get 2 cosine omega e to the minus j omega. All right, so you may say that, oh, we recognize, all right, we know, now we have h of omega equals magnitude of h of omega e to the j angle of h of omega. So what are you tempted to say? You are tempted to say that this is minus omega and this is 2 cosine of omega. But this is not going to be true when this is negative. If this is negative, that cannot be, that doesn't match. So case 1, if cosine of omega is positive, then you can write that magnitude of h of omega is I'm thinking all right, I'm thinking maybe there's something we should write before. Magnitude of h of omega, we have it right away. Obviously, magnitude of h of omega, we have its absolute value of 2 cosine of omega. Because magnitude of this is 1. And magnitude of this is its absolute value. So this we have it right away. What is not easy to find is the phase, the angle. So what remains to find is this. But that is not straightforward. What you know is that you have h of omega equals this. So in fact, I can write it is 2 cosine of omega we are sorry. It's the first time I teach it this way. You saw me changing my way to teach. Actually, I'm just improvising now. It's the first time I teach it this way, and it's nice. If cosine is positive, then this match, so this will match. The two will match. All right. So, oh yeah, nice. I've been teaching in a not nice way for 18 years, and now after 18 years, I found the way to do it. So it's easy to see that h of omega is minus omega by matching, right? By matching. But if cosine of omega is negative, then we have a problem, right? We have a problem because this is not the same thing as this. But so how can we do? Okay, not straightforward. So in this case, this and that don't have the same sign, all right? So is it possible to rewrite this in this form? Oh, no, it's much simpler. All right, look. This is negative, okay? This is negative. You want to make it positive, right? So I make it positive. That's too easy, huh? So I'm not allowed to do that. But that's my trick, all right? I'm allowed to multiply by -1 here and -1 here, right? So this becomes so positive, right? So this becomes 2 cosine of omega, you agree? And this, I don't want to leave it like that. I want to put it in the form that looks like that. Can you do that? No. Plus 2 pi, it doesn't do anything. Yes. This is the same thing as e to the j minus omega plus pi. Huh? Because I want to get rid of the minus here. You see the minus sign? I want to get rid of it. You know that e to the j pi is minus 1. All right? Since, okay, if you don't see it, since e to the j pi is minus 1. All right, so now you can do matching, right? By matching, then you find the angle of h of omega is minus omega plus pi by matching also. So it's stupid, but it's the way it is. All right. Yeah, I'm saying it's stupid because it's just technical, right? It has nothing to do with intuition or whatever. All right. All right. But you know what? Also, I'm sorry, that's case 2. So I said it's stupid, right? But there's something else that makes it even more complicated. One extra constraint. Yeah, I know. Okay, there's no code, so okay, it's I'm going to save this. Oh, it doesn't see the, okay, it's internet problem, I guess. So there's an extra constraint, which is that we like to have the angle of h of omega is typically chosen between minus pi and pi. You know that the angle is defined modulo 2 pi. You know that? So, but we like to choose it between minus pi and pi. So you see, when we pick when we pick h of omega like that or like that, I mean angle of h of omega like that or like that, it is not guaranteed that it will be between minus pi and pi. But we will see it when we do the plotting. All right, so plot, we are going to plot cosine. So basically, because of this discussion, we are going to plot cosine of omega, and depending on the sign, we'll plot this or that. I'm hesitating between doing the plot in front of you or just copying from last semester.
Plot.
You are nice with me. All right, so I do it. I don't copy. All right, okay. Because I hate plotting sinusoids. Okay. Yeah. Yeah. Okay. I will just work with this. Okay. Okay. Do you like this cosine? Yeah, I could. Yeah, I could have done that. All right. So you recognize cosine. Between 1 and minus 2. So cosine of omega maybe I should plot that in a new page. Okay. But anyway, what happens is that from this you can see what is magnitude of h omega, which is absolute value of 2 cosine magnitude of h omega is 2 times. So what we are going to have 2 here, and also, oh, I forgot, this is minus pi over 2, pi over 2. But since it's absolute value, then this becomes positive. Yeah. I cannot select. Okay. This goes like that. And all right, so next we need to plot angle. So what I'm going to do is that I'm going to copy that to the next page, because I will need this graph to discuss when cosine is positive and when it's negative. So I'm going to remind you that angle of h of omega is minus omega when cosine of omega is positive, and minus omega plus pi when cosine of omega is negative. Oh, by the way, once you are done with a plot, you should check whether this has the properties that we expect. What did we say about the magnitude response, the property of magnitude response? it should be even. Remember? Is that the case? All right, so do good. Even. Now, let's plot magnitude of h omega. No, angle of h omega. Now you can see that you need to divide the region in two regions. Where is the region where cosine is positive? It is between minus pi over 2 and pi over 2. So the between these two lines, let me plot minus omega. So minus omega is this line, right? Can you see the dotted line, or is it too? Yeah. Okay. Good. But I'm going to highlight. I'm going to highlight only the part that is valid in blue. The part that is valid is like that. Oh, that's funny. And we need to complete the graph. We need to plot what is outside. So you so the complementary region is here and there. There you need to have minus omega plus pi. So minus omega plus pi. So pi is here. Minus omega plus pi is going to be this line. So I would say as a result that minus omega plus pi should be this segment followed by this segment. So the total curve will be, in fact I should, all right, maybe I should lower this. So the total curve would be this with a jump here, this, and then another jump, and then here, like that. Question is that, so we expect angle of h omega to be what? To be what symmetry? Odd. Is that odd? Is that odd? No, it's not. So one thing you can see is actually this h omega is not between minus pi and pi, because minus pi and pi is between, all right, so the minus pi and pi in amplitude is between here and there, and you can see this one is between minus pi and pi, but this one is above pi. However, you remember that we can define reminder, this is defined modulo 2 pi. So we can afford to add or subtract 2 pi until, so add or subtract 2 pi until angle of h over omega is between minus pi and pi. Then, so now a vector of length 2 pi. So this is a vector of length 2 pi, right? So what I'm going to do, I'm going to lower this function by this vector. And if I do that, I'm going to copy and paste. I get this segment. I get this segment. And then to validate my answer, I'm going to highlight it in blue. All right. I'm going to simply add so to validate, I'm going to say put it in blue. Is that blue? No, it's not blue. It's dark blue. I validate this one and I validate this one. In fact, you can see by geometry that this is actually minus, this is actually minus pi over 2, and this is pi over 2. All right, is that odd? Yes. Okay, sorry, it's technical and interesting, right? But I teach it because before I wouldn't teach that. I would let the student figure out in the homework, but then I can see that it's a disaster, so I do it, but it's boring and it's just technical. All right, so but the nice thing about these plots, I mean, the especially the magnitude is that so application whenever magnitude of h over omega is 0, then h over omega is 0. For example, let's say let's put it on omega naught. Then, so if, okay, maybe I'm going to write it in this way. If there is a frequency omega naught such that magnitude of h of omega naught is 0, which you can see in our example at pi over 2 or minus pi over 2, then what do you conclude? You conclude that then h of omega naught is 0 itself. And then that tells you that if you input this sequence, then what do you get here? Yeah, it's so easy that you don't dare to say it, but somebody said it. You get 0. So we say that e to the j omega naught is cancelled by the system. I never know if I should put one L or two L's. But if you don't know how to spell it and are afraid to get shot, you can look for another word like eliminated or filtered out. Filtered out. Right? Or eliminated. You can say eliminated.
We lost half the point in the exam because our word was
Or you can say blocked by the system. Or maybe you can say stopped. No, not destroyed. Shot. No, it's too violent. Any other word you want to say? Actually, eliminated is, I will put it last because this is not very much used. Halted. Okay. Let me tell you a suggestion I heard, like terminated. But the most common expression will be cancelled or filtered out. Right, filtered out, especially filtered out. All right, so this is a common concern in communication. E312, you want to be able to get rid. You want to be able to get rid to certain frequency components, right? For example, why do you want to do that is when you combine several signals together and you want to separate them. That's a way to do it. All right, so this is the attractive part about signal processing, is that you can add signals together, and yet you're able to separate them again. And that is fundamental to communications. Imagine, you know, the air, you have electromagnetic waves. Wow, this air is super crowded with so much. You don't see it, you don't feel it, you cannot touch it, but in the air there's zillions of signals. Yeah, here, going through my hand. You see, like going to my tablet. You see, I can put my body around it, it goes through my body, and my tablet receives, you know, yeah, I mean, it's actually higher frequency than, no, the gamma is even higher. Right. Yeah, yeah, there are some concerns that those electromagnetic waves could be cancer causing or things like that. So maybe I shouldn't put my body around this. But So this is fundamental to communication. All right. I find this is the amazing thing about communication and signal processing. This possibility to separate. But what you learn in communication is the separation of signals by frequency, right? By frequency. But you know that this is old now. This is old technology. Because now you can separate signals by other means than frequency. That means you can even have signals that are in the same frequency, and yet you can still separate them. All right? But it's like what we call orthogonality. Yeah. Frequency is only one technique to generate signals that we call orthogonal, but orthogonality is a much more general concept that you can have with signals, and it's something that I used to teach at Columbia at the graduate level. It's like other ways to separate signals. In fact, in communication, maybe is there an undergraduate course called digital communication? No, no. You have to go to the graduate level, right? But in digital communication, you have this type of signal combination and separation. No, because the modulation itself is based on frequency, yeah. But it's more like before the modulation, you can already add signals together, and yet you can separate them eventually. I mean, this is the exciting part about signals, but I cannot teach that. I teach a little bit of this now currently in my next class, EE for digital signal processing, a little bit. Okay. Okay, I just wanted to give you some motivation about why we like to plot magnitude of H over omega. In fact, if magnitude of H over omega naught is equal to 1, then we say that e to the j omega naught n is past in magnitude. In magnitude because it's past rigorously. It would be past if h of omega naught is 1 in complete value. Now we say it passes in amplitude. In amplitude, you preserve the amplitude. Okay. I'm ready to go to the next paragraph. All right, so the next paragraph, you have 75% chance to have several questions on it at the final exam. So, no, actually 100%. So the next paragraph, you have 100% chance to have even several questions about it, or I mean some questions about it at the final exam. All right. So you may want to switch on your turbo brain now. All right. That means you enhance your perception, and then after that you can sleep if you want. All right. So I'm going to specialize in the magnitude response of feedback systems or feed-forward feedback systems. Now, if you like, time to apply your knowledge about frequency response on the systems that we learned in chapter 2. We want to plot the magnitude response of a system of transfer function g of z equals this All right, so now you can see that even if I said that the emphasis of the exam is on the last chapter, it has to be comprehensive. Because, again, we are going to have elements of chapter 2 in it. You cannot escape. All right. So, how do we do that? So first, it's two steps, all right? So first, what is the frequency response? It is g of omega, which is g of z, where z is e to the j omega. All right, so I could write it, right? Okay, I'm going to write it. It gives you and then magnitude response. Magnitude response. It is g of omega equals its magnitude okay, plot g omega for omega in minus pi and pi. You agree? Right? If you just try to do that, it's like committing suicide. All right. So the difficulty of this lecture is that I'm going to teach math without math. Let me tell you, math without math is much scarier than math. Let me tell you why. Okay, so this is the case where you die if you try, all right? Because basically, at least there's a simplification that students often forget, is that often students, they try to simplify the fraction before taking the magnitude. So this will make you die even earlier. If you want to have something simpler, a first thing is to say that the magnitude of the ratio is also the magnitude of the numerator divided by the magnitude of the denominator, which is already simpler. All right, you are not going to divide complex numbers, but just divide real numbers. So you take the magnitude separately. All right. So, but even that is you are going to die, because a magnitude of a sum of complex exponential is crazy, because it's you know, the magnitude squared is complicated. The magnitude squared of a sum is complicated. All right. So we are going to be forced to do math by physical understanding. That means math without formulas. No, it's not logic. It's physical understanding, physical perception. So, because what you typically learn in math has little insight. It's just formulas and mechanical. But here because there's not going to be any formula, we'll have to do it physically by a physical understanding of what the formula is going to give you. By pure, insight. All right. So, no, not logic this time. Logic is chapter 1, but here it's not logic. It's like physical interpretation of a mathematical formula. What happens is that often students in I will say in this country, sorry, is that when they see a formula, they want to put numbers right away. But by putting numbers, once you replace numbers, you no longer know what has been the action of the numbers together to give you the end result. That's a problem. You have to be used to not replace numbers in a formula, but think in terms of the magnitude of the parameters without numbers. Saying that, this parameter is the one that will have the stronger action on the whole formula. Because this one is multiplied by this, and by effect of multiplication, it has this effect or that effect, right? This is what I say, physical interpretation of a formula. And this is often a weakness of students here. Because they are too much used to just putting numbers. And then in the end, when you put numbers, you no longer see what was the action of each number with each other. You plug in, and then you use calculator, and then you it's like I give you two numbers, a plus b, and you replace a by something and b by something, you add, you get a result, and in the end, if I say, okay, which one was the bigger number, then you say, I don't know, because I already performed the addition. All right. So, okay, okay. So there is no simple transformation. So I'm not going to say simple transformation. I'm going to say there is no simple closed form expression. Okay, I'm looking for another word. Tractable expression. Tractable expression. But let's say general tip. Analyzing magnitude of a plus b is difficult. It's difficult when a and b are complex. It is much easier. It is much easier. It is much easier to analyze magnitude of a product because this is this times this, and this is multiplication of two real numbers. Isn't that much simpler? Isn't that much simpler? All right. So, of course, so I'm not going to. Okay. So I'm not going to simplify notation. We are going. Okay. To simplify notation, we are going to keep working with g of z. You see, g of omega is complicated to write because this is much more complicated to read than this. All right. So we're going to keep on working with g of z, but by thinking, okay, this is capricious. By thinking of, so remember z was a smiley face. This time we are going to think that z is a complex number in the complex plane by thinking of z as a complex number. All right, then g of z becomes a complex number. Becomes a complex number, a complex function. And then we just say that then g of omega is g of z. In fact, g of omega in magnitude, it will be magnitude of g of z after z is restricted to the unit circle. All right, so z is already looked at as a complex number, but when you are looking at g of omega, you will restrict z to the unit circle. Okay, we restrict z to unit circle. All right, so first analyze magnitude of g of z for z in the complex plane. So now this is a real number. All right, this is real and non-negative. This is a function from complex plane to real numbers. So g of z in magnitude is a function from a plane, to real numbers. How can you represent such a function graphically?
The complex. Oh.
It's a magnitude.
Oh.
So z is a complex. you can think of it as part of the complex plane, which you can think of as a horizontal plane.
So maybe you can represent it three-dimensionally, where every so the Z complex numbers are each one of them is going to have a magnitude, and that magnitude is the real value that it takes on, right? So if you have
So you represent that in 3 dimensions, and you get an object in 3D, right? Can you give the nature of this, a name for the nature of this object?
It's like a curved plane.
That's not the, there's a better word. There's a better word.
Surface.
Yes!
Oh.
Everybody understand that? No? No, you don't understand that. Okay, the difficulty to teach that is that everything done in 3D is a problem because you need special glasses to see in 3D, all right? So, I'm going to simulate 3D. Okay, suppose f of x is a function from R to R. How do you represent it? How do you represent it? You represent it like that. Yeah? That you understand? Okay, that you understand. Now, what's the difference between this and this? The difference is that Z is not a real. It's 2-dimensional. All right? So what I'm going to do, I'm going to, okay, so now you have to make an effort of understanding what I'm doing, what I'm going to draw as something that is in 3D. Here I'm representing something that represents a horizontal plane in perspective. So I wish there could be some depth, but understand this is like a horizontal plane, and this is a vertical line. All right. So imagine that this is this horizontal plane, which I'm going to write like that. I do as if it. Do you watch soccer on TV? They have these flat ads on the lawn. Yeah, I'm imitating them. All right. So imagine that this is complex plane. All right. So this will be the real part, and this will be the imaginary part. You get that perspective, right? So any point Z will be any complex number Z will be a point on the horizontal plane. But I want to represent, so here X is any value on the real axis. All right, so I say real axis. How do you read f of x? How do you read f of x? Is the vertical stick. All right, so you know that. F of x is the vertical height. All right, so here f of z, magnitude of g of z is also going to be a stick like that. All right, so I'm going to put an arrow, and that is f of x. Here I'm going to put an arrow, and that is going to be magnitude of g of z. Do you see it's the same thing, all right? But as you move x and you follow f of x, you get the curve. I'm going to do the same thing, but z can be moved in 2D. So it's going to scan the whole plane. And you follow the tip of this arrow, and you get what? A surface. All right, so I don't know. You can understand what I'm drawing here? This is, hey, what did I do? So this is a surface. This is a curve. There's an E, right? And this is a surface. All right? But eventually we are not going to be interested in magnitude of G of Z. Eventually, we are interested in magnitude of HR omega, which is magnitude of G of Z, where Z is on the unit circle. So the unit circle, okay, the unit circle is here, all right? So I'm going to plot it in perspective again. Okay. Okay, let's see. Oh, it works. Hey, look at this. It's exactly, you understand that this is a horizontal, you understand that this is a circle in the horizontal plane. And then, but you're interested in omega, okay? So omega will, again, it's the first time I teach in this way. So e to the j omega, the omega will be a certain angle like that. And that is going to be e to the j omega. But you're not interested in this point. You are interested in the G of Z. So this is Z. Okay, I'm going to say this is Z. Z equals e to the j omega. And magnitude of G of Z will be a stick, right? It will be a stick. It will be a stick. Okay, magnitude of, so magnitude of G of omega will be, magnitude of G of omega will have a value, the height, that is function of omega. But then we are going to have omega going from minus pi to pi, right? So we are going to have omega going from minus pi to pi. So you are going, so this point is going to cover the full circle. And then in this way, you are going to, okay, now I have to plot something funny. This is going to be like on the surface. It will be like some curve like that on top of the circle on the surface. And then what you do is that you have to understand that it lives on a cylinder. A cylinder, all right? Oh, sorry. We need. No, it's not a cloud. It's actually, it's not a cloud. It's actually like a lace, a shoelace, which is in the air. And then what you do is that you cut it here, you unfold, and then you get a magnitude of J omega. So do you see what it takes to do math without math? Right? Are you ready for the challenge? Because we are going to do that for like explicit fractions. All right. Okay. So on the table I have returned homework 8. Now homework 9 is, for those who are late, is postponed to Wednesday because I forgot to cover enough material. But you can have your homework 8 back